Go.
Okay.
Yes.
All right, went live on YouTube and allowing them in. Show is yours. Rock and roll.
All right. Hey there. Welcome to another presentation in our Destination Space 2021 series. Come on in, and we're gonna introduce our speaker for today in a few seconds. All right, so today, Destination Space 2021, we're gonna be presenting an overview of the Mars entry, descent, and landing phase known as EDL. Today we have an amazing presenter. Her name is Dr. Anita Sengupta, and she is currently a professor of astronautical engineering at USC. Dr. Anita Sengupta will be sharing an overview of the Mars entry, descent, and landing phase, which we call EDL. Dr. Sengupta was a senior aerospace engineer at NASA for 16 years, and she led the development of a supersonic parachute for the Mars Science Laboratory Curiosity rover, the design of a Mars ascent vehicle, Mars sample return mission, a Venus lander mission, and an experiment for the International Space Station. She is currently conducting research on spacecraft and aircraft propulsion technologies. Please help me with a virtual welcome of Dr. Anita Sengupta. Dr. Anita Sengupta, please, thank you. Thank you for joining us today. We all look forward to your talk.
Thank you so much for having me, and good afternoon to everybody out there in the virtual space. And it's wonderful that we can connect virtually right now so we can talk about the amazing things that are going to happen in just a few days with the landing of the Perseverance rover. So today I'm going to talk about engineering the red planet with a focus on my role on the Curiosity mission and expertise with regards to entry, descent, and landing, but I'll also give you some background information as to the motivation behind why we explore Mars. But since all of you are students at different phases of your student career, thinking about what you might want to do next, I wanted to give you a little bit of a background on me and what motivated me to become an aerospace engineer. Ever since I was a little kid, I loved science fiction, whether that was Star Trek or Star Wars or science fiction that I read in book format. And I knew that I wanted to teach myself to be able to create these new technologies, to create these worlds that had amazing transportation systems that enable us to go across star systems to be able to find potential alien civilizations. And so I chose to become an aerospace engineer. My dad was a mechanical engineer because I really wanted to create a future that I imagined it to be. And that's what engineering allows you to do. And in terms of my background, my motivation was very much science fiction. I am an immigrant myself. I moved to the United States when I was 3 years old with my family from the United Kingdom. I got my bachelor's, my master's, and my PhD in aerospace engineering. And I worked 10 years after my PhD at NASA's Jet Propulsion Laboratory. But one of the things that you have to think about in the course of your career is that you can't just have like a single track. You have to have a trajectory with balance. So in addition to my work as an engineer, I also am a professor and a teacher, and I am also very active in a variety of different areas. My hobbies are actually flying. I am a pilot. I ride a motorcycle, and I do scuba diving, and I try and do as many enjoyable, exciting things which somehow seem to be related to technology as I can. And these are just some of the pictures from the course of my career. So I started off actually working on the development of launch vehicles or rockets to get things into space. And then I moved on to the development of communication satellites, which is communicating using spacecraft orbiting Earth. And then I moved over to NASA and worked on the development of deep space propulsion systems, sending a spacecraft to the main asteroid belt, and then on the development of the entry, descent, and landing system for the Curiosity rover that you can see me standing in front of. Then I had the opportunity to take on a leadership role to actually lead a mission to develop a payload for the International Space Station. The part of your career as you progress through it, both in school and in college and beyond, is to recognize new opportunities that you see and kind of, people like to say opportunity knocks, and to go through that door of a new and exciting opportunity when it presents itself, because it allows you to have a lot more fun and a more exciting career as a result. But the other thing, which I think is also important, is that it's good to increase your leadership skills. So I spent many years focused as a technical engineer, but I also spent many years focused as a manager, as an executive at a Hyperloop technology company, and now as an aviation entrepreneur, where I actually have founded and owned my own company developing technologies needed to make aviation more sustainable, for example. So you do have to lead by example in life, and you can take that from a career perspective, from a leadership perspective, and from a community service perspective, for example. And I chose to study engineering because I love science, but what engineering is applied science. So it allows you to take the tools of math and science and create new technologies that can solve some of the world's challenges. And a great example of that is today, currently with the COVID-19 pandemic, because of biotechnology, we now have these vaccines to be able to protect people from the COVID virus. So if it wasn't for that hybrid of science and technology coming together, we would have had a much more difficult time getting through the current pandemic. And now we can see a light at the end of the tunnel, and we're moving forward. But one of the highlights of my career was definitely working on the design of the entry, descent, and landing system for the Curiosity rover. And I'm not going to show you the full video, but I'll show you a portion of the video which describes some of the challenges associated with landing a rover the size of a small car on the surface of another world. And the video is called 7 Minutes of Terror because it takes approximately 7 minutes from the atmospheric interface, going at a really, really fast speed, slowing down, and eventually landing safely on the surface of the planet. So hopefully...
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
A parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we...
Sorry about that. I accidentally clicked through it.
During entry, the vehicle is not all...
Apologies.
And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage away to a safe distance from the rover.
So at the very conclusion of that, of course, is the successful landing of the Curiosity rover, and that was conducted in August of 2012. And almost that same identical landing system is going to be used by the Perseverance rover. So I encourage everybody to download the full video, which is 7 Minutes of Terror. You can find it on the NASA website, or if you Google it, you can probably find it as well. But to give you a little bit of a background of why do we explore Mars, of course, being able to design a system like that is really exciting and really cool and really difficult. But we explore Mars for two specific reasons. One is to understand how the planet evolved, and the second one is to learn more about the planet so one day we can send future human explorers there. And the reason why we're so interested in it from a scientific perspective, though, is that at the beginning of the formation of our solar system, Venus, Earth, and Mars were actually very similar to each other in terms of having an atmosphere with some oxygen in it, and in terms of having water on the surface. But over the course of the past several billion years, the planets have evolved quite differently from each other, where Venus, which is the orange-looking planet on the left, has a surface temperature of around 470 degrees centigrade, which is very, very hot, and a surface pressure 100 times the surface pressure of Earth. Mars, on the other hand, which is one planet out from us, has a surface temperature which is quite cold, in the minus 70 degrees centigrade region, and it has a surface pressure of only 1% of what we have here on Earth. So you can see that these two planets are so different from Earth, which is quite comfortable and quite a nice place to live. So we want to understand from a scientific perspective, why is it that these planets evolved in this way? And what this really means is that climate change is a planetary level phenomena. We've seen it on Venus, we've seen it on Mars, and we're also starting to see it here on Earth. But the other reason, of course, we explore Mars is to eventually one day send people there. And we'll talk about some of the technologies associated with how to land people on the surface of Mars and how to have them survive on the surface towards the end of the presentation. But when we look at the history of Mars as a planet, it's had a very active geological history, which means that we can learn about the planet's past by sending spacecraft to orbit the planet, as well as rovers and landers to make measurements on the surface of the planet. And just to give you some examples, the picture on the upper left here is Olympus Mons. It is an extinct volcano. It's actually the largest mountain in the entire solar system, and it exists on Mars. And the fact that it's there means that at some point in Mars's past, it had a lot of volcanic activity, but it appears to have stopped. Similarly, Valles Marineris, which is the picture on the bottom, is Mars's version of the Grand Canyon, but I think it's about 6 to 7 times as deep. And we know that the Grand Canyon on Earth was formed by water flows. So Valles Marineris probably was formed by a combination of water flows as well as wind erosion on the surface of Mars. But what happened? Why does there appear not to be that much volcanic activity? What happened to all the water? And one theory is actually that there was an asteroidal impact on Mars many billions of years ago, which shattered the molten magnetic core, which disrupted the magnetic field, which allowed the atmosphere to be ripped away by in-space radiation. So that's a hypothesis, and that's a hypothesis which scientists test by sending spacecraft to orbit Mars, as well as rovers and landers to explore on the surface. So these are the reasons why we conduct these missions from a scientific perspective. A really important finding, both from a scientific perspective and to support future human exploration, is to be able to understand what happened to the water. Is there still water present on the surface of Mars? And it turns out that there is actually water flowing in the form of a wet mud called a putative water seep on Mars today. And these are images which are taken by a spacecraft known as the Mars Reconnaissance Orbiter that shows these sort of dark black streaks, which we have confirmed spectroscopically that contain water in them. And so if we in the future land people on the surface of Mars and we have them land in one of these regions, they could actually make use of that water for eating, for washing, for drinking, and to split it up to make hydrogen and oxygen, which is also rocket fuel. So we learn a lot on the evolution of the planet by having these spacecraft that orbit from above. And these are discoveries that everybody engages in, from the scientific community to the citizen science community. And believe it or not, the discovery that these dark flows contained water was made by a student, a graduate student from Georgia Tech. So one of the most challenging things, though, to do in space missions is to land on the surface of another planet. And so we've done that successfully a total of 8 times with the U.S. space program, hopefully another time coming up on Thursday of this week with the Mars 2020 Perseverance rover. It was done first in the 1970s with the Viking landers. It was done again in the 1990s with the past Pathfinder Sojourner rover, and it was done again in the early 2000s with the Spirit and Opportunity rover. Phoenix Lander in the mid 2000s, and then of course, Curiosity in 2012, Insight in 2018, and now Mars Perseverance coming up in 2020. And all these images that you see here are pictures that are taken by the rover of their landing sites after they've landed. And they're really interesting views because you can see it looks like a desert world, but it doesn't look so dissimilar from our own desert locations on the planet Earth. And so we have to develop very complicated systems to be able to land successfully on the surface of these planets, which we'll talk about a little bit more. But there's a lesson to be learned here, which is that in this picture, you can see the evolution in rover technology over the course of the past several decades. And on the lower left, you see a small sort of Tonka truck-sized rover, which kind of looks like a toy, which was sent in the 1990s, followed by a much larger lawnmower-sized rover in the early 2000s, which is Spirit and Opportunity, and then of course followed by Curiosity, which is seen on the right-hand side, and Perseverance essentially is the same size and looks the same way. And so we've been able to make bigger and bigger rovers over the course of time. And the reason why we do this is because a larger rover can carry more scientific equipment on the back and can conduct a more interesting science mission. So it's just like if you were thinking about if you were going to move from one house to another house, would you put all of your stuff on the back of a bicycle, or would you put it in the back of a large truck? You would put it in the back of a large truck. So it makes a lot of sense to be able to increase our rover size, to increase our rover's capability. And so this is what the space exploration program is all about. So you have to think about this in the context of your own career, is that you can make each chapter a building block to the future that you could eventually achieve, maybe in the STEM fields or in something else. So the Curiosity mission and the Mars Perseverance mission is to understand whether or not the planet was once habitable in the past and whether or not it could still be habitable today. And it does that by making a series of measurements of the atmosphere, of the rocks and the soil to determine the geology and the geochemistry, and also the surface radiation levels, which are really important to understand whether or not if people can survive on the surface, and or do we have to make unique radiation shielding technologies moving forward. So when we, as the entry, descent, and landing team, design the entry vehicle, we have to pick a landing site. And the landing site is selected by the science community getting together with the engineering community to find a place which is interesting to land, as well as a place which is safe to land. And so for Curiosity, we land in a location called Gale Crater. And for Perseverance, they're landing in a location called Jezero Crater. And the reason why those locations were selected is because we believe in the past they were both sites of ancient water bodies. So where better to look for evidence of past habitability than in the base of an ancient lake or river? The same would go for here on Earth. So these are the kinds of sort of thought processes which are used to select landing sites. But they're very scientifically interesting, but they're also very difficult to land, which you can see in this picture here, which is a 3D view of the Gale Crater landing site. And what's so difficult about it is that in the middle of the crater is a mountain, and on the sides of the crater are the crater walls, which means that if you are the rover coming in to land, you have to land in sort of a bullseye location so that you don't smack into the mountain in the middle and you don't smack into the crater walls on the outside. So that means you have to have a very precise landing system from so far away on Earth to be able to land in that small region, that small black ellipse or circle that you can see in this image. And so that what was done for Curiosity, and that's what is being done for Perseverance on Thursday afternoon of this week. And the way this is done is using something called an entry vehicle. So the picture that you see here on the left, it's kind of this odd looking bowl shape, is actually a type of airplane. It doesn't look like an airplane, but it is an airplane because it's able to generate aerodynamic lift. So it doesn't have a wing, but it does have a shape which generates lift, which allows you to land the entry vehicle more precisely. But what it ultimately is trying to do, though, is generate a lot of aerodynamic drag. So aerodynamic drag is probably something you haven't heard of before, but I can give you a really simple example of what it is. If you're going down the road in your car on the highway and you open the window and you put your hand out of the window, you feel this like strong buffeting wind force on your arm. That's aerodynamic drag. So what the entry vehicle does is it has this big bowl looking shape to generate all this aerodynamic drag to slow itself down. It's trying to dissipate its energy. It's trying to slow down. And that is the basic principle by which you land in a planetary atmosphere. So I'll give you a short video that I will try and talk over. It might be a little loud. So you're coming into the atmosphere at around 20,000 kilometers per hour. That's very fast, 30 times as fast as an airplane, 5 times as fast as a bullet. You slow down with aerodynamic drag, then you reach a point where you have to deploy a very large parachute, which is the portion of the mission that I worked on. The parachute also creates aerodynamic drag to slow you down even further, down to around 1,000 kilometers per hour. Then at that point, you've actually hit terminal velocity, which means you don't go any slower. So you cut away the parachute, and then you do the rest of the descent on a system called the Sky Crane, which has a series of 8 rocket engines, which are pointing towards the ground and firing towards the ground to help slow you down even further. When you get about 60 feet or so above the surface, the rover is started to lower on a series of 3 ropes, and then it continues to slow down, continues to descend towards the surface, and eventually is able to touch down very slowly, just a few miles per hour, wheels down on the surface. Those 3 ropes that you see are cut, and the little spacecraft above turns to the side and flies away and crashes a safe distance away. And the rover has landed. That technique was used for the Curiosity rover in 2012, and it's also being used for the Perseverance rover on Thursday of this week. It worked very successfully in 2012, so it made sense to use that same system or the Perseverance mission coming up with a few additional tweaks to make it even more precise and even more accurate in terms of where it's able to land on the surface. So you can see a very complicated system. And what makes it even more complicated is that you're not able to test that system end to end here on Earth, because Earth is so different in terms of higher level of gravity, a different atmosphere. So the first time you really test that system end to end is actually on landing day on Mars, which is why it's so complicated. So this is kind of a 2-dimensional view of how that entry, descent, and landing system works. It starts off with slowing down on this heat shield, that odd-looking bowl shape, where you get to really high temperatures on the front of that heat shield, and then you do the remainder of the supersonic descent on a very large parachute, which gets you to below the speed of sound. Then you cut away the parachute. Then you do the remainder under the descent on the retro rockets, and eventually the Sky Crane, which lowers the rover to the ground on tethers. And that system, once again, has worked in the past with Curiosity and will be used again on the Mars Perseverance mission coming up on Thursday of this week. But just to give you a little bit of understanding of what it means to be an engineer to work on one of these missions, each one of those phases is led by an engineer. So I led the development of the parachute system. And so the parachute, you've probably heard of parachutes before. Parachutes for Mars aren't that different from parachutes for Earth. They just happen to have to be much stronger than the parachutes that we have here on Earth, because you go a lot faster because the atmosphere is very thin. But the parachute is basically made out of a textile or cloth material. It's very lightweight, but it's also very strong. And the one that we developed for Curiosity and the one that is also being used for Perseverance is 70 feet in diameter. So it's actually quite large. You can think about it that if you inflated it, it carries the equivalent of 3 school buses. So that's very big if you think about it that way. And that big area is used to generate a lot of aerodynamic drag to slow you down. This picture gives you kind of a good graphic of how big the parachute is for Curiosity and Perseverance, where there's an SUV truck on the left-hand side, a person in the front here, and here's the fully inflated parachute. So we went out and tested these parachutes in the desert in Idaho before we ended up, putting them on the mission, because that's what you do as an engineer. You test to make sure that everything works out okay ahead of time. So this is a nice video that I'll show you of one of the parachute tests that we did. And what you're seeing is you're looking up now at a helicopter which is deploying this parachute, and the parachute is inflating. It kind of looks like a large jellyfish almost, and it creates this nice big drag area, and it slows down. But it does experience a lot of force, a lot of load on it because of all of the air which is pushing against the inside of the cloth material that you see. So this is essentially what it looks like on Mars, slightly different, obviously not a blue sky, but it operates in the same principle, in the same way. And this is a picture of me in front of the parachute when we tested it several years ago for the Curiosity mission. And once again, very similar to the parachute, which is being flown for the Perseverance mission. And I like to show this picture because whenever you do these activities, it's not just one person working on it. It's a large team of people working on it. And so this was the team who I led and worked with for many years in the development of the parachute system for the Mars Curiosity rover. So teamwork is required to solve something as challenging as this. Now, I think what's so interesting about the Curiosity mission, the Perseverance mission, is it has many new technologies which are needed for future robotic exploration as well as future human exploration. And one of the key technologies is an advanced power system, where the rover is using a nuclear power source to generate energy to keep itself warm, to be able to communicate back to Earth, as well as to run its scientific equipment and to drive. And so this power system is called an MMRTG, which stands for Multi-Mission Radioisotope Thermoelectric Generator. So there's a plutonium-238, which is a radioactive material, which is generating heat, and then that heat is then converted into electricity. So you can think of it like a battery, which is made with this radioactive material, and it generates heat all day long, generates electricity all day long, and that lasts for many, many decades. So it's a very important technology in order to facilitate Mars exploration. So as we're thinking about Perseverance, which is landing in only a few days, the large portion of its journey is now complete, which was the interplanetary cruise from Earth to Mars. And depending upon the trajectory you select, it takes roughly 7 to 9 months, which is a really long time, you know, from the perspective of the students who are in school right now. It's basically the length of a school year. It's also the length of time between a human sloth, a human being gestation period, and a sloth gestation period. And so it is a long time, but you can also think about it that you'll be busy doing all kinds of tasks if you're on board the spacecraft, if you're the human being going to Mars. So you'll be probably busy for that 7 to 9 months. So the last video I wanted to show you is related to what it looks like for the rover to land on the surface of Mars. And for Curiosity, we actually put a camera on the underside of the rover. So as it was descending towards the surface on Mars, this is the real video of what it saw. And so what you're going to see now when I play this video is the heat shield falling away, which is the front of that odd-looking salad bowl. And now the rover is looking down towards the ground to the base of the crater in which it's about to land. You can see kind of a tan region with some pock marks on it, which are actually meteorites that go through the atmosphere on Mars, don't get fully burned up and crash on the bottom. And you also see like a darkened black region, and that's evidence of prior volcanic activity, like I showed you Olympus Mons earlier in the presentation. You can also see the camera is moving back and forth, and the reason for this is that when you're under a parachute, even here on Earth, you tend to rock back and forth, so the rover is experiencing this sort of like rocking, oscillating motion as it descends underneath the parachute. You can also see that we're getting closer to the surface now, which means all the features are becoming more visible and larger. But soon you'll see that the rocking motion stops, and that's because the parachute has been cut away. And then we're doing our descent on retro rockets. And so we're going to see that now, and things are looking smoother. Now we're kind of flying off to the side. It's engaged in something called the divert maneuver, which may or may not be used for Perseverance depending upon hazards that it's trying to avoid on the ground. And now we're getting closer and closer, and the sky crane is about to start. You'll see a rover wheel fall into view. You'll start to see some soil getting kicked up because of the gases from the engine interacting with the ground. There's the rover wheel into view, and now we're getting closer and closer to the surface. So now we can't see the ground because there isn't enough light getting into the camera to be able to show us that. But after that maneuver was executed all autonomously from the ground, no human being with a joystick or anything like that, the rover was commanded to send a picture of itself. And this is where it landed on the ground. This is the landing site, and you can see Mount Sharp in the middle there, and you can see the shadow of the rover, which ironically looks a little bit like a transformer, which I think is kind of cool. And my favorite part about this image is that on the right-hand side is the location where Curiosity landed, and it looks so similar to the desert regions here in California or in Arizona or in Nevada. So there's so many similarities between Earth and Mars. Of course, Mars doesn't have a nice oxygen-rich atmosphere like we do, but it does have very similar surface geology type of features. And one of the really important parts of being good at math is being able to run numbers, run calculations, and make simulations. And so this graphic, if you look in the lower right-hand side, has a red ellipse, or sort of like a wide circle, and in the middle of that is a white box. So our engineering calculation said that we were going to land somewhere in that red ellipse, and we ended up landing in that white box because we did a really good job with our engineering calculations. And Perseverance is doing the exact same thing in terms of trying to land in that red ellipse and as close as possible to the center so that it doesn't have to drive as far to get to an interesting location. Another really interesting image that we collected from Curiosity mission is we were able to take a picture of the rover descending underneath the parachute on landing night, which is what you can see here. So this is a real image of a spacecraft taking this picture from orbit, and hopefully we can see something similar for Perseverance coming up. I won't go through this in the interest of time, but when we make all of these surface measurements, we're trying to understand what the composition of the rocks and the soil are. And we do this using a technique called spectroscopy. So that sounds like a big word, but really what it is that if you fire a laser at a material and you can turn it into a gas, it generates a light fingerprint, and that light fingerprint actually tells you what it's made out of. So in the graphic on the bottom here, you can see the presence of many different elements. There's aluminum, calcium, silicon, all of the building blocks of matter that we have here on Earth, we also find on Mars. And so these are the types of measurements that the robotic geologist, the rover, can make on Mars and send that data back to us here on Earth. And similarly, we have a weather station on board Curiosity. There will also be a weather station on board Mars Perseverance, and we collect data on the temperature, on the pressure, on the radiation levels, and we use all that data to create a model of the atmosphere, which is required for us to safely land on the surface, because we need to understand how thick is the atmosphere, what temperature is it going to be as we're descending towards the surface. All of that goes into our entry, descent, and landing modeling simulations and calculations. And then finally, one of the most important pieces of information which was collected for Curiosity, and Perseverance is going to collect similar information, is the evidence of organic molecules. Organic molecules, if you remember from your science classes, are the building blocks of life as we know it. And so we did detect the presence of methane on the Curiosity rover, and the Perseverance rover is carrying an equipment to make measurements of biosignatures, which are kind of like chemical fossils. So you've probably seen fossils of dinosaurs. So these are chemical fossils, which is certain imprint of what chemicals would look like that are created during biological processes, and it's going to take a look at that for Perseverance. So for the near future, which is in the next few years, of course, we have Perseverance coming up, landing on Thursday, which will then engage in a 2-year scientific measurement mission, looking at biosignatures, making oxygen using Martian CO2, collecting a sample for future mission return, as well as collecting a lot of information on the rocks and the soil. But my very favorite technology demonstration aspect of Perseverance is the Ingenuity Mars helicopter, which I think you'll be getting a presentation on the next few weeks. This is the very first electric aircraft ever to be flown on the surface of another planet. It will fly for 90 seconds per day, fly above the rover, take images, and transmit that data back to Earth so we can get a better understanding of what the landing site looks like, as well as help the rover make decisions on where to drive next. One of the really important features associated with the entry, descent, and landing for the Perseverance mission is something called terrain relative navigation. So I showed you that video before of the rover descending, taking those pictures. We did that for a very specific reason on the last mission. We wanted to show that we could collect those images at a fast enough rate, process them at the fast enough rate so that we could take a look at, oh, this picture says that we're actually here on the ground. And this is a technique called terrain relative navigation, which is going to be used on Perseverance on Thursday to help it avoid any hazards as it approaches the ground by taking those pictures that I showed you before. So the very last topic I want to leave you with is what technology is needed to put the first human beings on Mars. So those students who are on the call right now or listening on YouTube, one of you could potentially be the first person who sets foot on the surface of Mars and potentially even stays there for longer on a Martian colony. And so one of those technologies is a spacecraft that will allow us to transit between Earth and Mars and then re-enter Earth's atmosphere. And this is currently being worked on. It's called the Orion vehicle. It's being worked on at NASA Johnson Space Center in concert with Lockheed Martin and Boeing and Northrop Grumman and several other companies. And so this is something which has already been flight tested. So hopefully it will start to fly within the next 5 years or so for the Artemis mission, for example. One of the biggest challenges, though, we have going forward to send people beyond low Earth orbit, beyond the International Space Station, is to protect us from the radiation environment. So we know that the radiation environment is too high on the surface of Mars if we went there just in a regular spacesuit. So we're going to have more radiation protection material, both for the trip in interplanetary space out to Mars, as well as on the surface of Mars. And so whether or not those radiation protection are new materials that have yet to be developed, or I like to turn to science fiction, a magnetic shield, such as what's used on Star Trek, These are things that have to be developed. These are things that the engineers of your generation will be working on to allow human beings to explore further into space. Another one, which I think probably everybody likes, is the development of robots that have intelligence or artificial intelligence. These are being developed by NASA, but they're also being developed by private companies throughout the world for a range of different applications. But the reason why we want smart robots is because human beings don't have the strength of a robot. So if we can protect human beings and only use them for the really, really important jobs when they go out and do EVAs on the surface of Mars, for example, we can have the robots do some of the more mundane jobs like setting up the habitats or, drilling and things like that. So that's where you can see how that would be useful. And of course, everybody likes to know, what am I going to eat when I go to Mars? We will bring some food with us, but we'll also likely grow our own food on the surface of Mars. And so this could be done under the ground using special plants, which are designed to use very little oxygen and use a lot of CO2 and produce a lot of oxygen with photosynthesis, and have fiber optic light fed into these greenhouses, basically, subterranean on Mars, to generate food that the people who live on the surface of Mars can eat. And guess what? We already are doing some work in that area on the International Space Station with the development of the veggie habitat, where they're growing lettuces in space inside the International Space Station to show that we can basically farm food in space. And so all of this work would carry over nicely to future Mars exploration. So the first human on Mars will probably live in very small habitats like this. And we'll have to be there for extended periods of time on the surface, 6 months to potentially 2 years in these pressurized habitats, but also do some extracurricular activity. And you've probably heard a lot about the term sustainability here on Earth. We have to use sustainability techniques on Mars as well. It's called living off the land, ISRU, in situ resource utilization. So we have to generate power from the sun. We have to protect ourselves from the radiation, potentially by using Martian soil and going under the ground. We can access water, like I showed you earlier before, and we can convert that water by splitting it up into hydrogen and oxygen, which are rocket fuel, or we can create another rocket fuel called methane, and then we can also grow plants there. So just to wrap it up, so we have time for some questions at the very end, I leave you with a question of, would you want to live on Mars? Would you want to be one of the first colonists on Mars? And I hope you do. And I'm giving this presentation, and Andres and everyone here is participating in this because we want to encourage you to become scientists and engineers so you can take the path, take the reins over from us, and eventually send yourself to Mars and beyond. So thank you. So now I'll take questions.
Thank you, Doctor. So we're going to open up the mic for a few students because it looks like we have a lot of wonderful questions. So right here, let's ask Alan Ramirez. Go ahead, Alan.
What happens the inside gets hot? What will happen to the rover?
That's a great question. So that is a real concern. And so what we do is we design the entry vehicle to have a heat shield on the front of it so that it absorbs all of the heat, so the heat doesn't get into the interior of the cabin. So fortunately, the rover experiences kind of a room temperature environment because all of that heat, which is generated on the outside, is burned away by the heat shield. But that same kind of system is used when the astronauts re-enter Earth's atmosphere, for example, would have to be also implemented here on Mars for robotic explorers as well as for the future people. That's a great question.
Thank you. Okay, how about Juan Daniel? Go ahead, ask your question, Juan Daniel.
What happens of the humans when they get there? They cannot breathe.
Oh, if they can't, well, so human beings definitely need to be in an oxygen-rich environment, and they need to be in a pressurized environment. So for the first Martian explorers, they would either have to walk on the surface in spacesuits, just like you see them do when they're doing EVAs outside the International Space Station, or they would have to live inside of a habitat which is pressurized with a mixture of oxygen and nitrogen. And everywhere in between, they'll always have to be in this pressurized environment, either in a spacesuit or in a habitat. But yes, it's true. Human beings without these kinds of special equipment around them would not be able to survive on the surface. So they have to be in spacesuits. But the good news is that because there is some pressure on the surface of Mars, 1% of the surface pressure that we have here on Earth, the spacesuits don't need to be as big and as bulky as the spacesuits which are used in the hard vacuum of space that people on an International Space Station is. So it'll be easier for you to walk around. And on the surface of Mars, the gravity is 1/3, which means that you will be able to walk, so you won't be floating around everywhere. Great question.
Thank you. We see Adaya Vasquez. Adaya Vasquez, go ahead.
I don't know if my mic's working correctly, but if it isn't, then you know. But the question is, what advice would you give a student like me that may consider going through the same career path as you?
Oh, so definitely do it, number one, because it's probably one of the most fun things you can possibly do is work on the space program, because it just challenges you in a positive way, and you just learn new things every single day. So in terms of what you would do in your middle school and high schools, you would take as many math and science classes as you can. So if you can, try and take pre-calculus, try and take calculus, try and take biology, chemistry, and physics. Maybe join some of your school's clubs when they reopen again, like the math club and the science club. If you can, try and do sort of like summer research opportunities in the sciences, and all of that kind of builds up your resume, which helps you with your application to university. And then when you're considering a job in university, when you're considering a degree in university, you can study so many different fields that allow you to work in the space program. You can study aerospace engineering, mechanical engineering, electrical engineering, computer science, astrobiology, physics, chemistry, astronomy. All of those fields are applicable to be able to work in the space program, because it's a multidisciplinary field. It doesn't just require one type of engineer. Like, I'm an aerospace engineer because I like the design of systems that generate lift and things like that. So I focus on fluid mechanics and thermodynamics, but there are so many different ways that you can enter the space program. So any engineering discipline, any computer science discipline, pretty much any science discipline will allow you to have a career path in the space program.
Thank you. We have Tron and Juliet. Go ahead and ask your question, Tron and Juliet.
If Perseverance bumps into a canyon wall while landing, will you be able to retrieve it?
That's a great question. So at this point, no, we wouldn't be able to pick up the rover. But one of the things that Perseverance is doing is it's actually collecting a sample of Martian soil and rocks and putting it in a little canister off to the side so that a future mission can go and pick up that canister, put it inside of a rocket, and send it back to Earth. So when the first human explorers, perhaps you two, go to the surface of Mars, you could go and walk over and drive over to one of the rovers and check it out. And it probably won't be operational by then. It'll probably last for 10, 15 years or so, but it'll still be there. But there are no plans to bring the rovers back because they're too heavy, but there is a plan to bring back a sample, which Perseverance is collecting.
Thank
All
you.
right. So let's all please help me give Dr. Anita Sengupta a virtual round of applause. What an incredible presentation. Thank you very much. I know that your presentation has inspired many. It's going to be on YouTube, so it's going to continue to inspire those that could not make it today. Again, this week they're on break, but I know that they know about you and Dr. Anita, and I know that they're going to come and check out your presentation. I loved it. So inspiring.
Thank you for having me, and it was wonderful to see the students, and thank you for the wonderful questions.
Yeah, absolutely. So again, remember that tomorrow we have Dr. Fernando Mir Hicks. He's going to be presenting. And then on Thursday, we're going to be live waiting for the Mars 2020 Perseverance landing. And our MC is going to be Dr. David Desmarais. So come back tomorrow, come back Thursday, which is a very exciting day for not only for NASA, but for the whole world. I know that everybody's excited about the landing. Thanks a lot, everybody. Thank you again, Dr. Sengupta. Take care, stay safe,
Bye.
and we'll see you tomorrow. Bye-bye.